So welcome back to homework number 3. This one should be a pretty quick one. Um, let's again take just a couple little notes before we start with this homework assignment. With scientific notation, all that we're doing is moving a decimal to the left or moving a decimal to the right. If we move the decimal to the left, our exponent is going to be positive. If we move our decimal to the right, our exponent is going to be negative. And the reason for that is because if we're trying to get back to what the original number was, and we moved the number to the left to get back to the original number, we have to move to the right, which makes the number bigger, which makes the exponent positive. If we're trying to get back to the original number and we have to move the decimal to the left to do that, that means that we're making the number smaller, and that makes the exponent negative. I'm not sure how much sense what I just said makes without any context, but that's what we're going to demonstrate in number 1 and number 2. So we have the number 754,000. They're asking us to write this in scientific notation. So let's go ahead and do that, recognizing that our decimal is right there. I could put 0.000000000 and it would still represent the same number. To get to scientific notation, we only need one number in front of the decimal. And in order to accomplish that, we're just going to basically count how many spaces we have to move the decimal to do that. So there's 1, 2, 3, 4, 5. I had to move the decimal 5 spaces to the left in order to get one number in front of the decimal. To get this number back to being what it would be in its original form, I would have to move the decimal to the right, and doing that would make it a positive exponent. So the final thing for this is going to be 7.54. Again, the big thing is to only have one number in front of the decimal. And then we will have times 10, because each one of these little spaces that we moved is a power of 10. So like if you think about place value, tens, hundreds, thousands, 10,000s, hundreds, thousands, each one of those is a multiple of 10 of the one before it. And so then we just count how many spaces did we move that decimal. 1, 2, 3, 4, 5. And so that, to get back to the original number, we would have to move the decimal 5 spaces to the right. So that makes the exponent positive that we put on this one. And so just to test that out, let's write it out. 7.54. And then let's move the decimal 5 places to the right. 1, 2, 3, 4, 5. And in all these empty slots, we just need to drop a 0 in there. Well, look, we ended up with our original number, 754,000. So that worked. Okay. Now for moving in the opposite direction to represent numbers that are very, very tiny. What we're going to do is we need one number that is not 0 in front of the decimal place. And so I've got 3 zeros, 9, 7, 3. And so now, instead of moving the decimal to the left to get one number in front of the decimal, we need to move it to the right. So we'll move to the right 1, 2, 3, 4 spots. And remember, I only want one whole number in front of the decimal. So that whole number is going to be 9, and then the decimal 7, 3. Times 10 again, because each move that we made was a power of 10. And then this time, our decimal is going to be negative, because to get back to the original number, we need to move the decimal to the negative, or to the left, which is a movement in the negative direction. And we count again how many spots we move the decimal. 1, 2, 3, 4. And so that's going to be 10 to the negative 4. Let's go ahead and come over here and test that. 9.73. If I move the decimal to the left 4 spots, 1, 2, 3, 4, and I fill the empty slots with 0, that does get us back to our original number. So it works. So I'll go ahead and box in my answer of what you would actually put into Alex in these cases. That's what you would put into Alex. That's what you would put into Alex. these test things over here are just to make sure we did it correctly. All right, so for number 3 and for number 4, it's the exact same identical process. I'm not going to go through the test and the explanation and all that stuff. If you need to hear it explained again, go ahead and watch number 1 and 2 again. But we need to represent this number 0.000000. How many are there? I don't know. 1, 2, 3, 4, 5 zeros. And I have one too many. So that many zeros. 653. And so again, if you can count, you can do scientific notation. So 1, 2, 3, 4, 5, 6 places to the right. So we're going to have 6.53 times 10. And to get back to the original number, I need to move to the left. So it's going to be a negative exponent. Let's count the number of movements. 1, 2, 3, 4, 5, 6. I had to move 6 spots. So that number in scientific notation is going to be 6.53 times 10 to the negative 6. Because if I move the decimal 6 places to the left, I would get back to my original number. Similar with part B right here. Standard notation, we're going to be changing this like I did in my test up here from scientific notation to standard notation. So 2.6 times 10 to the 5th. Basically what that means is to get to the original number or to standard notation, we need to move that decimal place 5 slots to the right. So we will take 2.6 and go to the right 5 spots. 1, 2, that was a terrible drawing right there. So 1, 2, 3, 4, 5. Fill those with zeros. So we will have 4 zeros, and so our finished number is going to be 260,000. So a fin whale can weigh up to 260,000 pounds. That's a lot. Alrighty, I'll pause there so you can take a look at that if you need to, and then I'm moving on to page number 2. So the next piece for us here is to calculate whatever this is, and so this is going to be identical to the work that we did in homework number 1 and homework number 2. Where we need to recognize that we can multiply these two pieces, and we can multiply these two pieces. Now the 10 is something that we're almost going to treat like a variable. So it's not going to be 10 times 10 and make 100. It's going to be 10 to the 7th times 10 to the 5th. And so we're going to add those exponents. So to get started, we're going to multiply the 3 and the 1.3, which gives us 3.9. Then we're going to treat that 10 like a variable, and the exponents 7 and 5 make 12. So we end up with 3.9 times 10 to the 12th. I'm going to pause really quick and just make sure that I did that correctly. I'll be right back. Yeah, buddy. Schlegel's on fire today. That's correct. Alrighty, so moving on, we're going to squeeze down to number 5, and I do believe that this is the last one. Again, this is going to be just like the work we did with exponents previously. We're going to treat that 10 like a variable, and then just do the laws of exponents with it. And so we're going to write our answer in scientific notation. I'm going to do this one, and then I'm going to have to check on Alex and make sure of how exactly Alex wants it. I'm assuming that they're going to want it the way that I have it, but we will see. So what we've got to do is recognize that we can't simplify 6 over 5, but that 8 and 5 will cancel each other out or divide out and leave a 3 in the numerator. And so what we end up with here is we will have 6 times 10 to the 3rd in the numerator, and that whole thing will be over 5. And so that's where I would stop personally, and I'm actually going to fix that 3 because it looks kind of wacky. But I'm going to run really quick and check on Alex and make sure that that's the way that they're going to ask you to do it, and then I will be right back. Okay, so it looks like what Alex is going to want you to do is to go ahead and divide that 6 by 5 and get 1.2. and then recognize that what remains is still going to be times 10 to the power of 3. So for Schlegel, either one of these would be acceptable, but I do believe that when you are working in ALEKS, it's going to want you to go to the place of turning that fraction into a decimal and ending up with something that looks like that. So with that, everyone, I hope that this was helpful, and I hope that you have an awesome day.